In this question we're told bromine monochloride dissociated on heating according to the equation. In an experiment, 0.9 moles of bromine monochloride was heated in a 5 litre vessel at a certain temperature until equilibrium was established. The amount of free chlorine in the mixture was found to be 0.4 moles. Part 1. Write the equilibrium constant expression for the reaction. So to write an equilibrium constant expression, what we need to do is write the concentration of the products over the concentration of the reactants. And our products are what are on the right hand side of the equation. So square bracket Br2 with Cl2 multiplied all over the concentration of BrCl. Now because the coefficient of the BrCl is 2, we need to put a power of 2 there. So the coefficients become powers. So that's our equilibrium constant expression finished. For part 2 then, what we need to do is to calculate the value of the equilibrium constant for the reaction at this temperature. So that means using my ice table down in the bottom left to get my equilibrium concentrations that I can then substitute back into the equilibrium constant expression to get the value of the equilibrium constant. So now what I need to put into this table are moles per litre values. But as we can see here in the question, we have a 5 litre vessel. So all of my mole values are moles per 5 litres. So to get to moles per litre, I'm going to have to divide them by 5. So my BrCl to begin with, this 0.9 moles of BrCl. So I have 0.9 moles of BrCl, and that's in 5 litres. And that's also initial. That's at the beginning of the experiment. So to get that into moles per 1 litre, I need to divide that by 5. And 9 divided by 5, 1.8. So, 0.9 divided by 5, 0.18. So 0.18 moles per litre BrCl. It's that value finished. The next one we have is until equilibrium was established, then the amount of free chlorine in the mixture was found to be 0.4 moles. So that's 0.4 moles of chlorine, Cl2. Now that's after equilibrium was established, so that is an equilibrium value, not an initial value. But again, it's in the 5 litre vessel, so to get moles in 1 litre I need to divide it by 5, and 0.4 divided by 5, we get 0.08 moles per litre of Cl2. And that's everything I've been told, isn't it? It is. So now we're going to fill those into our ice table. So in the top row I need to put in the chemicals that I have. So I have BrCl, I have 2 of them. Then on the right hand side I have Br2 and Cl2, and they have coefficients of 1. Now just to make everything extra clear, just so I know where the arrow is in my equation, I'm just going to make this into a double line, just so I know where they're separated. And then I can start filling in. So my 0.9 moles of bromine monochloride is an initial value, so I'll put that in initial in my BrCl, and that is 0.18 because it's the moles per litre value I have to put in. Okay, so that's after coming from over here. Then I have to fill in my equilibrium value for my chlorine, and that's going to be this value here, 0.08. Now what else can I fill in on this table? If we look at the initial values, we only had 0.18 moles per litre of the BrCl. That means I had 0 for the rest of my initial values. Now if I look at the table again, what I can see is that I had an increase of 0.08 moles in the case of chlorine. That also means that for bromine, because chlorine and bromine are 1:1 in this equation, I also had an increase of 0.08. And then respectively again, for the BRCL, I must have used up 0.16 moles because there is a coefficient of 2. So it's 2:1 with the rest of them. So I have twice as much, 0.16, which is twice 0.08. Now I can fill in the rest of the equilibrium row. So for the BR2, I started with 0. I have an increase of 0.08. So 0.08. For the BRCL, I began with 0.18, went down by 0.16, so I have 0.02 left over. And from that we can then substitute the values in the equilibrium row. So these values back up into my Kc equation. And what we see is that Kc is equal to, so for bromine, that's a 0.08. For chlorine, it's also a 0.08. And for BRCL, it's 0.02. And don't forget that squared up the top. And then this will evaluate out to be 16. So the Kc value, the equilibrium constant for this reaction at its particular temperature, is 16.